Section: Introduction. In this section, we present evidence indicating that many internal activations of language models are sparse and can be represented as linear combinations of vectors that correspond to meaningful features. However, it is often challenging to identify which vectors are meaningful. Sparse autoencoders, SAEs, offer a promising unsupervised method for this task and have been shown to discover interpretable and causally relevant directions. If successful, this approach could enhance various applications of interpretability, such as identifying and correcting hallucinations, explaining unexpected model behavior, and preventing manipulation by autonomous AI agents. Despite their potential, sparse autoencoders are still a developing technique, with several unresolved issues that need to be addressed before we can fully utilize them. These include validating SAEs, measuring their performance, training them efficiently at scale, and applying them to real-world tasks. Therefore, there is a pressing need for further research in both industry and the broader community. Unlike previous interpretability methods, SAEs can be costly and complex to train, which limits the scope of interpretability research. While there has been valuable work on smaller models, most studies involving SAEs on modern models have concentrated on specific layers and often used proprietary models, making it harder for the wider community to build upon this research. To tackle this challenge, we have trained and released the weights of Gemma scope, a comprehensive and open suite of jump-ReLU-SAEs across all layers and sublayers of the Gemma 2 models, including the 9 billion and 2 billion parameter versions, as well as selected layers of the larger 27 billion model. We have made these weights available under a permissive license on Hugging Face to facilitate and accelerate research by others in the community. Training Gemma scope was a significant engineering challenge, resulting in over 400 sparse autoencoders and more than 30 million learned features, trained on a substantial amount of text data. We utilized over 20% of the training compute of GPT-3, saved around 20 PB of activations, and generated hundreds of billions of parameters for the sparse autoencoders. We believe that having a comprehensive suite of SAEs is crucial for advancing interpretability applications, such as circuit analysis, and for scaling up to larger models. This may help us understand complex phenomena in larger models, like chain of thought or in-context learning. In the following sections, we will provide background on SAEs and jump-ReLU-SAEs, details about our training process, evaluations of the trained SAEs, and a list of open problems that Gemma scope could help address. Section Summary. In this section, we discuss the potential of sparse autoencoders, SAEs, to identify meaningful features in language model activations, which could enhance interpretability and address issues like hallucinations and unexpected behaviors. We introduce Gemma scope, a comprehensive suite of jump-ReLU-SAEs trained on various layers of the Gemma models, and emphasize the need for further research to overcome challenges in training and applying SAEs effectively. Section: Jump-ReLU-SAEs. In this section, we focus on jump-ReLU sparse autoencoders, SAEs, because they offer a slight improvement over other methods and allow for a varying number of active latent variables at different tokens, unlike top-K SAEs. The jump-ReLU activation functions as a gating mechanism, combining a shifted heaviside step function with a standard ReLU. Here, the jump-ReLU has a learnable threshold parameter, and it keeps pre-activations the same above this threshold while setting them to 0 below it, with each latent having its own learn threshold. For our loss function, we utilize a squared error reconstruction loss and apply an L0 penalty to directly regulate the number of active latents. The L0 penalty and jump-ReLU function are piecewise constant concerning the threshold parameters, so we employ straight-through estimators, STEs, for training. This requires an additional hyperparameter, the kernel density estimator bandwidth, which influences the quality of the gradient estimates used for training the thresholds. We train our SAEs on activations from Gemma 2 models, using text data similar to that of the pre-training text for Gemma 1, except for one suite trained on the instruction-tuned model. We only gather activations from tokens that are not beginning of sequence, end of sequence, or padding. After generating activations, we shuffle them into groups of about 32. While we believe a perfect shuffle wouldn't greatly enhance results, we haven't verified this systematically and encourage further exploration in future work. During training, we normalize activation vectors to have a unit mean squared norm, which helps in transferring hyperparameters reliably across layers and sites. After training, we rescale the SAE parameters to eliminate the need for input normalization during inference. We train SAEs at 3 locations per layer, as shown in our figures. We focus on the outputs from attention heads before the final linear transformation and RMS norm, the MLP outputs after RMS norm, and the post-MLP residual stream. For attention output SAEs, we combine the outputs from individual attention heads into a single SAE. We index layers starting from 0, meaning layer 0 is the first transformer block after the embedding layer. For optimization, we maintain the same bandwidth and learning rate across all training runs. We implement a cosine learning rate warm-up over the first 1000 training steps and use the Atom optimizer with a batch size of 4096. We also linearly warm up the sparsity coefficient during the first 10,000 training steps. During training, we parameterize the SAE with a pre-encoder bias, which we later incorporate into the encoder parameters for inference. We ensure that the columns of our parameters have unit norm by renormalizing after each update and project out the gradient components parallel to these columns before the Atom update. We initialize the jump ReLU threshold with a specific vector and use uniform initialization for our parameters, ensuring each latent vector has unit norm. The biases are initialized to 0 vectors. Section Summary. In this section, we focus on jump ReLU sparse autoencoders, SAEs, which improve upon other methods by allowing a variable number of active latents per token. We describe the jump ReLU activation function, our squared error reconstruction loss with L0 regularization for sparsity, and the training process involving normalization and optimization techniques to ensure effective learning across different layers and locations. Section Topology. In this section, we describe our training process for sparse autoencoders, SAEs. We primarily use TPUv3 in a 4x2 setup, while some wider SAEs are trained on TPUv5P in either a 2x2x1 or 2x2x4 configuration. For sharding, we train SAEs with 16.4K latents, maximizing data parallelism and tensor parallelism through Megatron sharding. We observe that for smaller SAEs, the time spent transferring data from host to device exceeds the time for the update step, making data sharding advantageous. In contrast, larger SAEs benefit from bigger batch sizes, which enhance arithmetic intensity by minimizing transfers between high-bandwidth memory and virtual memory. The design of SAEs allows for minimal device-to-device communication with Megatron sharding, but data parallelism incurs a costly all-reduce of full gradients. Therefore, we suggest selecting the smallest degree of data sharding where the host-to-device transfer time is slightly less than the update step time. For instance, with optimized step times, we can process a batch for a 131K width SAE in 45 milliseconds on 8 TPUv3 chips, achieving a model flop utilization of about 50.8%. Regarding disk storage, we save all activations on hard drives as raw bytes in 10 to 20 GB shards, using 32-bit precision. Storing 8 billion activations for a single site and layer requires around 100 terabytes for Gemma 2.9b, and about 17 petabytes for all sites and layers of both Gemma 2.2b and 9b. The total storage is even higher since we also train some SAEs for 16 billion tokens and on Gemma 2.27b, plus we maintain a buffer of extra tokens. Although this requires significant disk space, it is more cost-effective than regenerating the data for each training session. For disk reads, since SAEs are shallow models with short training times and we use activation vectors instead of integer tokens, we need high data throughput. For example, Training a single SAE on Gemma 29B without data loading bottlenecks requires over 1 GB per second of disk read speed. This need increases when training multiple SAEs on the same site and layer, especially with different sparsity coefficients or during hyperparameter tuning. In our evaluation, we assess the trained SAEs from various perspectives. We note that there is currently no agreement on a reliable metric for the quality of a sparse autoencoder or its learned latents, which remains an area of active research. Unless stated otherwise, all evaluations are conducted on sequences from the same distribution as the SAE training data, specifically the pre-training distribution of Gemma 1. For our methodology, we trained SAEs with different sparsity levels by adjusting the sparsity coefficient while keeping the dictionary size fixed. We then plotted curves to show the reconstruction fidelity at various sparsity levels. We measure sparsity using the mean L0 norm of latent activations. To assess reconstruction fidelity, we employ two metrics, calculated on 2048 sequences of length 1024, after excluding special tokens during aggregation. Our results indicate a trade-off between sparsity and fidelity for SAEs in the middle of each Gemma model. We found that delta loss is consistently higher for residual stream SAEs compared to MLP and attention SAEs, while the FVU is roughly similar across sites. We hypothesize that even minor errors in reconstructing the residual stream significantly affect language model loss, whereas larger errors in reconstructing outputs from MLP or attention layers have a limited impact. Additionally, prior research suggests that language models experience lower loss on later token positions. Thus, we investigate how an SAE's performance varies along the sequence length. Similar to our previous analysis, we track reconstruction loss and delta loss across different sparsity settings without aggregating over sequence positions, again masking out special tokens. Section Summary. In this section, we describe our training setup for sparse autoencoders, SAEs, using TPU configurations, emphasizing the importance of data and tensor parallelism for efficiency. We also evaluate the performance of SAEs across various sparsity levels, noting the lack of consensus on quality metrics and highlighting the trade-offs between sparsity and reconstruction fidelity. Section Result. In this section, we examine how reconstruction loss changes based on position for 131K width sparse autoencoders, SAEs, trained on the middle layer of Gemma 29B. We observe that reconstruction loss starts close to zero and increases quickly for the first few tokens. For attention SAEs, the loss consistently rises with position but levels off after 100 tokens. In contrast, MLP SAEs reach a peak around the 10th token before gradually decreasing. We think this happens because attention mechanisms are better at managing long-range dependencies in text, which is more relevant when there is ample prior context, while MLP layers focus on local patterns, like n-grams, that require less context. Similar to attention SAEs, the loss for residual stream SAEs also increases steadily but plateaus more gradually. We find that the patterns are similar across different models, layers, widths, and sparsity coefficients. Next, we look at how delta LM loss changes with sequence position. The high noise levels in delta loss measurements make it hard to accurately assess the impact of position, but we notice that the loss is slightly lower for the first few tokens, especially in residual stream SAEs. We also explore the effect of SAE width. When keeping everything else constant, wider SAEs learn more latent directions and achieve better reconstruction quality at a given sparsity level compared to narrower SAEs. This suggests that we should use the widest SAEs possible for downstream tasks. However, we also see indications that this idea may have limitations. The phenomenon of feature splitting, where latents in a narrow SAE seem to divide into multiple specialized latents in wider SAEs, suggests that wider SAEs do not always utilize their extra capacity to learn a broader range of features. It seems that the sparsity penalty during training encourages wide SAEs to focus on common combinations of existing features rather than using their additional capacity to learn new ones. It remains unclear whether this is beneficial or detrimental for the effectiveness of SAEs in downstream tasks. To support research on how the properties of SAEs change with width, we train and release a feature-splitting suite of mid-network residual stream SAEs for Gemma 22B and 9BPT, with matching sparsity coefficients and widths ranging from 45K to 59K in powers of 2. These SAEs are trained with different sparsity settings after layers 12 and 20 of Gemma 22B and 9B, respectively. We also discuss the trade-off between sparsity and fidelity. Similar to previous sections, we compare fidelity versus sparsity curves for SAEs of different widths. Regarding latent firing frequency, we present frequency histograms for 4K SAEs across a range of widths from 52K to 50K latents. We calculate the firing frequency of each latent over 20,000 sequences of length 1024, excluding special tokens. We note that as the number of latents increases, the mode and most of the distribution shift towards lower frequencies, although there remains a group of ultra-high frequency latents, which we have also seen in top K SAEs but not in gated SAEs. We also investigate the interpretability of latents for a subset of the SAEs included in Gemma scope. Previous studies evaluated latents using human raters and language model-generated explanations. We summarize the key findings here and refer readers to section 5.3 of that work for a detailed methodology discussion. Both human evaluations and LM explanations focused on jump ReLU, top K, and gated SAEs of width 131K trained on all sites at layers 9, 20, and 31 of Gemma 29B. We present the human raters' assessments of latent interpretability and the correlation between LM simulated activations and actual activation values. We find little noticeable difference among jump ReLU, top K, and gated SAEs in both metrics. Lastly, we provide additional training for ITSAEs. Previous research has shown that SAEs trained on base model activations can accurately reconstruct the activations of IT models derived from these base models. We find further support for this by comparing the Gemma scope SAEs with several SAEs we trained on the activations from Gemma 2B9B. We train these ITSAEs using the same pre-training documents as the other SAEs, adding Gemma's IT prefix for user queries and responses. Each SAE is trained to reconstruct activations at all token positions except for the user prefix, as these tokens have much larger norms and are consistent across documents. We also release the weights for these SAEs to facilitate further research into the differences between training SAEs on base and IT models. Section Summary. In this section, we analyze how reconstruction loss varies by position in different types of sparse autoencoders, SAEs, and find that wide SAEs generally provide better reconstruction fidelity, although they may not always utilize their capacity effectively due to feature splitting. We also explore the interpretability of latents across various SAE architectures and provide additional evidence on the effectiveness of SAEs trained on base model activations compared to those trained on IT model activations. Section: Methodology. In this section, we evaluate the sparse autoencoders, SAEs, trained on the activations of the IT model. We generate 1024 rollouts from the Gemma 29B IT model using a random sample of the SFT data that trained Gemini 1.0 Ultra, with a temperature setting of 1.0. We then utilize SAEs trained on the residual stream of both the base model and the IT model to reconstruct these activations and measure the fraction of variance unexplained, FVU. Our results, shown in a figure, indicate that using SAEs from the PT model leads to a slight increase in cross-entropy loss, similar to the increase observed with SAEs directly trained on the IT model's activations. We also conduct further evaluations on Gemma 22B, focusing on FVU instead of loss, and include activations from user queries. Another figure reveals that the FVU for point SAEs is somewhat accurate, but not as compelling as the previous results. We hypothesize that fine-tuning involves adjusting existing features from the base model while also learning new features specific to chat, which may not significantly affect next token predictions. This could explain why the FVU appears worse than the loss increase, as the FVU is influenced by less impactful chat features. For future work, we suggest fine-tuning these SAEs on chat interactions to achieve lower reconstruction errors or evaluating them on multi-turn and targeted rollouts. Next, we perform a sparsity fidelity evaluation on various validation subsets of the pile to see if SAEs struggle with specific data types. Our findings show that SAEs perform best on DeepMind mathematics, likely due to its formulaic nature, while they perform worst on Europarl, a multilingual dataset. We believe this is because the training data for the SAEs primarily consisted of English text. Regarding low-precision inference, we train all SAEs using 32-bit floating-point precision. To reduce memory and computational demands during inference, we can lower the precision. This is particularly relevant for applications like circuit analysis, where multiple SAEs may be used simultaneously. A figure compares fidelity versus sparsity curves for both 32-bit and bfloat16 weights, indicating that switching to bfloat16 has minimal impact on performance. We aim to support the safety and interpretability communities with Gemma scope by advancing our understanding of interpretability and its role in making models safer. We present a list of open problems we hope to see progress on, which we believe Gemma scope can help address. These include deepening our understanding of SAEs, improving performance on real-world tasks, and exploring scalable circuit analysis. We express our gratitude to several individuals for their contributions to the project, including those who helped create an interactive demo, develop tools for researchers, and provide engineering and organizational support. We also thank our beta testers for their feedback and acknowledge the contributions of many others involved in this work. In terms of author contributions, Tom Lieberman led the report writing and evaluations, with significant support from Vikrant Varma and Lewis Smith. Senthoran Rajamanoharan developed the Jump ReLU architecture and contributed to the report. The SAE training code was designed by Tom and Vikrant, with contributions from Arthur Conmey. Janos Kramer played a key role in the interpretability codebase, while Neil Nanda coordinated the project and wrote the list of open problems. Anka Dragan and Rowan Shah provided leadership and advice throughout the project.